Hello, I am making a video to finish out these worksheets and to take a look at integrating many of the things that we've learned this quarter. This will help you brush up on the easier problems by working through challenges that integrate all these different areas of our learning. So we're going to start with a chemical equation between sodium hydroxide and phosphoric acid. So there's a little naming exercise. What are the formulas for those? What state of matter do they have, and what do they form? So let's complete and balance the chemical reaction first. And then we'll get into our stoichiometry question. Feel free to start working on that. Looking for the mass of sodium hydroxide required to neutralize a certain amount of phosphoric acid. So that would be a chapter 8 problem. Okay. Sodium hydroxide is a strong base, aqueous, plus phosphoric acid. Is H3PO4. It is a weak acid. All acids are aqueous. And when these react together, it's with a strong base, so that's going to react completely to form what? Write your products. Sodium phosphate. So there we'll look on the solubility rules. Sodium is rule number 1, so this is aqueous. There's our salt. And what's the other thing that we form in an acid-base reaction is water. I'll go ahead and give that a subscript. Is water aqueous? Nope, it's a pure substance. It's a pure liquid. Okay, let's balance it. We've got 3 sodiums, so we'll need 3 sodium hydroxides. Then we're going to get our 3 hydroxides, which are with our 3 hydrogens, so we'll need a 3 in front of the water as well. Okay, I'll move that up and start laying out the information that I need for that. All right, we need to know how many grams of sodium hydroxide will we need to react completely with 50 grams of phosphoric acid. All right, to line up your dimensional analysis for this, let me rewrite the problem. How many grams of NaOH do we need to neutralize 50 grams of, I'm gonna, maybe I'll write Pa for phosphoric acid. Yeah, does that work? Okay, give myself a little bit of room. So let's think about what we need for that. And I'm going to also label this Pa here. All right, let's see, we need to get rid of grams of phosphoric acid and go to moles, so we need that molar mass. So I'm going to go calculate that, and I like to tabulate that underneath here. Do we need it later? We don't need it later. Maybe it doesn't matter. Okay. Maybe you've calculated that already. let's see, phosphorus, what, 30, yes, 30.97. Plus 4 times 16, 97.994 grams of phosphoric acid in 1 mole. And what next? We need to cancel out moles of phosphoric acid and turn that into moles of sodium hydroxide. Using those coefficients, oh, we've got a 3 on top and a 1 on the bottom. All right, are we done yet? Let's see, not quite. We need to go to grams. So we will need that molar mass of sodium hydroxide. Okay, so 50 divided by 97.994 times 3 times that answer in my calculator, I get 61.225 grams of sodium hydroxide. And I will check my sig figs. Started with 3, we'll end with 3. Okay. Now, the next one, I'm going to go ahead and move this up a little bit. What volume? So I'm going to continue this table layout here. We want to know what volume, so how many liters, I could write it like that, how many liters of 0.144 molar sodium hydroxide is required. Oh, and this is a different question, so let me just cross that out so we're not confused. We've done that already. Okay. Is required equals 36.4 milliliters of 0. Oh, I got that in the wrong place. That's okay. 750 molar. Right, so I'm just using this table to lay out the question. In fact, let me erase the earlier question. There we go. Let me get my little erase tool. So I'm lining up these questions the way they're written here. So let me put my, oh geez. Okay, I'm going to put my little marker here so that you can see I'm lining it up under the equation right there. Okay, there we go. So I'm using this to keep track of what it is, the sodium hydroxide and the phosphoric acid. So maybe that's not useful. We can also just look at it from dimensional analysis. How many? Oh, and you know what else? Let's go ahead and do milliliters, yeah? How many milliliters of solution, and this is the NaOH solution, do I need to neutralize? So here's the is the equals. And there we have a volume and a molarity connected by of, so I'm going to start with that. 36.4 milliliters of PA solution. And I'm going to break out that capital M, that molarity, into moles on top and liters on the bottom. So that's going to be 750 moles of solute. So that's the H3PO4 per 1 liter of that solution. So I know I talked about a number, a unit, and a label, but sometimes we need more. Sometimes we need to say used up or excess or expected. So we're starting to see a couple more words coming into there. All right, let's take a look at our units. Canceling. There's, I'm going to cancel just the liters. Kind of doesn't matter. Maybe it's a little early to do this. We've got moles. So now what do we need to do? We need to get rid of moles of that phosphoric acid. And go to what? We need to change the label. So what do? Let's use that mole-mole relationship from the chemical equation to get to NaOH. All right, and that has a 3 in front. Now, a really common error is to divide by 3 or multiply by 3, get it on the wrong side, get it inverted basically. So if you keep track of your units, that will really help you because you can see that 3 needs to be in the numerator. That's one reason this is so much more powerful of a method than memorizing the steps. Just trying to make a little more room, right? Because what comes next? Milliliters, oh, liters, volume. You can multiply and divide by 1,000 if that's more comfortable. Here we're changing from phosphoric acid to sodium hydroxide. We're looking for milliliters. So you might take a look at this formulation right here, and what does that make you think of? When we have a molar equivalent, you might be thinking of that dilution equation. M1 V1 equals M2 V2. And from that we might say, okay, well I'm looking for the volume, right? That's why I kind of like to lay it out like this. That V2, the one we're looking for, is going to be M1 V1 over M2. So let's plug in 1 over the molarity, right? It's kind of like we're taking that molarity and dividing it out. So I'm going to break it out into your moles and liters. So this says 0.144 moles of NaOH. Oh, I didn't get my decimal. Okay. Is contained in 1 liter of solution. And that's the hydroxide solution, of course. Okay, so let's get back to that units, taking a look at the units. Here, look at that. We've changed our moles, canceled it out, and ended up with liters. But because I did not do any conversions, I have this milli kicking around and this liters here. So when I multiply those out, my answer is going to end up in milliliters. That's one thing that's nice about millimoles and milliliters is that if you put in milliliters, you'll get out milliliters from the dilution type of equation. Okay, so 36.4 times 0.75 times 3 divide 0.144 If you did a conversion, then you would multiply, you'd divide by 1,000 first, and then you'd multiply, oh, yeah, there you go. So I get 11.7936 milliliters, and we're not going to be able to measure it that precisely, but let's just take a look at the sig figs. We're looking at 3 all around. So about 11.8 milliliters. Okay, so that's bringing in that molarity consideration. And again, you'll probably see this again as a review in your other classes. So this is just developing how it all works together at this point. Okay, here is another one. This one's a little bit more practical. We're talking about calcium carbonate in limestone, and we're going to analyze how much is there using the hydrochloric acid. So what is the chemical equation? It's going to be the calcium carbonate plus hydrochloric acid. So first writing those formulas, then predicting the products, and then balancing. So go ahead and pause the video and work ahead on that. All acids are aqueous, and calcium carbonate is a solid, and I believe that comes up all the way in the carbonate rule, rule number 5. All right, that carbonate is going to be decomposed by the acid, so we're going to form CO2 gas plus water, which is a pure liquid when it forms like that. Oh, I didn't leave room for my balancing coefficients. And then what else? This is going to be the salt that's left over. That is calcium chloride. That'll have 2 chlorines. And rule number 3 has halogens are all soluble except silver, lead, and mercury. So this one is aqueous soluble. Oh, all right. We're going to need 2 of those chloride ions. Then, I think everything else is 1. Okay. So let's go back to figuring out what we're looking for here. We'll keep that equation. So limestone is a mixture. It's got calcium carbonate and other stuff. And we're trying to figure out how much is the calcium carbonate. So here is our amount of limestone. And it requires, so there's an equal sign of some sort, 2.50 grams of hydrochloric acid. Calculate the mass percent of calcium carbonate in the limestone. So let's take a look at what we're looking at. We're wondering how many grams of calcium carbonate in that mixture. So we can do this a couple ways. Oh, we've got the total volume, right? I'm sorry, it's not a volume, that's a mass. The total mass, of course. The total amount. So I'm constructing a mass percent right here. I know that we've got 3.50 752 grams total in that limestone. So then we'll take that times 100%, and that's the answer we'll get. So what we need to solve for first is that grams of calcium carbonate from these amounts. So let's lay out what we're looking for over here in our visual game plan here. We need to know how many grams of calcium carbonate if it took 2.50 grams of HCl. And I was wondering, why did we give it grams of HCl? Probably just to be consistent and easy, and maybe you haven't gotten to chapter 15 with molarity yet. But this would be a bit easier if it was molarity and volume. Right, but here we're going to have a mass, so we'll just need to do our molar mass instead. Okay, and then, you know what else? I'm going to erase these guys and scroll this up. There's our question. Okay. Go ahead and work it with dimensional analysis if that's what you are most comfortable with. And I am going to use the table method. This is, I'm going to put up my molar mass. So in the problem, I've got 0.06856 8 moles given. And then from that, I'm going to calculate how much calcium carbonate must have been in that sample using these coefficients. So I'm going to divide by 2 moles of HCl and multiply by 1 mole of calcium carbonate. All right, oh, we need our mole mass. 40.08 plus 12.01 plus 3 times 16. So moles times the molar mass will give us the grams back. 2.8. Okay, so I am getting 3.431, and that is just 3 sig figs. So I'm going to stop there. Oh, we have another calculation. Well, let me go ahead and underline this was 3, and this was 3, and this has a 1 next. Okay, so I'm going to plug that in down here. So that calculator answer, divide by 3.752 times 100 equals 91.45%. Okay, now it ends with a 5, which means that if you truncated this, it could have a big, it could flip that digit. So if we're presenting this formally, we would say, okay, that is about 91.5% calcium carbonate in limestone. Okay, now these are acid-base neutralizations, and they come in the next section of chapter 15. All right, what else? Here's another one. One more. This is going to be another one from that section. Acetic acid. What's acetic acid? Do you know that formula? And calcium hydroxide. Write the chemical equation. Then we've got masses again. Phooey, I want molarities and volumes. The student then evaporates the water that's formed and weighs the remaining solid. That's going to be that salt. Oh, does the solid contain only the salt? So this is a little bit like that yield idea. What else is in there? Is there anything else in there? Okay, so work through that and I will do the same. I like to write this out this way, just, not as standard. Oh, we need a parentheses there. There's 2 hydroxides. And that is a strong base. It's aqueous. Oh, and that's also in the solubility rules as an exception to rule number 10. All right, there's the acidic proton. It's an acid-base neutralization, so we're going to form water as a liquid plus whatever the salt is. In this case, that calcium is going to need 2 of those acetate ions. And I'll go ahead and put this 2 as a subscript so that it looks good. And acetate is always soluble, rule number 2. Now we'll balance. We must need 2 of those H's to connect with the OH's here to form 2 waters. Or you might have started here and seen that we have 2 of those acetate ions, and that's fine too. All right, in the next problem, we're going to start with 25 grams of acetic. I'll leave the labels off because I'm going to line it up. And 25.0 grams of calcium hydroxide. This is so much more fun when I have students with me. Because what do we even have to do here? What do you think of doing? Does the solid contain only the salt? How are you going to find out? Well, we're given 2 reactants. So the first thing I would do is run the limiting reactant problem and see how much do we expect. So let me just suggest that. How many grams expected? How will we know if there's only salt? Well, if there's only salt, then these would be in perfectly equivalent amounts, molar equivalent amounts. Because the masses are the same, it's very unlikely that that's the molar equivalent, which means that there's likely to be some excess reactant. And then it says, if not, explain what else is present. So that might mean calculate the extra amount. Okay, but I think from the way this is laid out that we're gonna get a little bit of scaffolding. Oh, that's for the excess reagent. Okay, so let's run the limiting reactant problem as outlined. So two parallel calculations. Pick the one that produces the smaller amount. Okay, so pause the video and work ahead on that. All right, I'm going to label my table. Given grams, molar mass, and I'm going to write given moles, because we always have to be in moles to work through that, through the columns on the chemical equation. Another reason this is nice, well, I mean, if you write all your dimensional analysis, then I can read your work and give you partial credit pretty easily. But a lot of students don't do that. But if you do it in a table that has this format and you include the units, then I can see really quickly if your molar mass is incorrect or something like that. Okay, I'm gonna pause here and make sure I indicate sig fig so I'm keeping track. Okay, so that's what's given, and then we're gonna figure out from here, oh, let me get another color. Yeah, how many moles could we get from that one, or how many moles could we get from that one? And that is if our limiting reactant is calcium hydroxide. Okay, and you can see they're equal because it's 1 to 1. On this one, we're going to divide by 2 and multiply by 1. This is moles we expect if, and only if, which is IFF, that limiting reactant equals acetic acid. All right, from there we're going to pick the smaller one. This one, acetic is limiting. And I do like to go back and label my equation just to give that visual cue. When you look at the equation, there's your limiting. Okay, let's set up the table. So this is where I had initially introduced the table method, but I didn't feel like, well, I mean, I knew we'd kind of run out of time. So I want to introduce the layout a little bit earlier, but it's really especially helpful here. Let's go ahead and take it all the way to grams. So now we know which one is limiting. We only need to take this one to grams. And I, turned that all off. Okay, 0.20815 moles. Oh, I didn't even calculate the molar mass. Okay, hold on. That is 40.000. Let's do the acetate part times 2 and then add the calcium. It'll just be a little quicker in the calculator that way. Okay, 58.036 times 2 plus 40.08. And I did those all in blue, so let me do that in blue here. All right, nobody's here to tell me if I got that wrong. So if you get a different mass here, go ahead and post to the forum. Okay, so there's our molar mass, and we have moles, so we're going to multiply those. Moles is in the denominator here, so when I multiply those, I'll get grams back. So times 0.20815. I was pointing to the other one. But here, I get, oh, I'm in blue, 32.50 grams. And that is my theoretical yield. It's expected. All right. So after reaction, I can go ahead and fill this in. We didn't really care about the product so much, but I'll go ahead and put this one in here. This is calcium acetate, a little easier to write out. And after the reaction, oh, well, initially we had 0. And after the reaction, we have 32.5 grams. Okay, before the reaction, we had 25.0 grams of acetic acid and 25.0 grams of calcium hydroxide. And then after the reaction, oh, we got to figure out how much got used up. So let me go ahead and change colors again and take a look at, we know this is limiting. So, oh, you know what I had written before was during the reaction. And then after. 0 grams left. Right, how do I know that's 0 grams? Because that's limiting. Right, I'm writing my line. Okay, so we have the grams. After the reaction, we know that this is 0 grams left because it's the limiting reactant. And we want to figure out the mass of reactants and products before and after. Okay, we'll go ahead and do this one. That's not quite right though, because these are aqueous, so there's some water. So let me just update this, say new water. The new water that's formed. Not the solvent water, but the new water molecule that gets formed from the reaction. Okay, so we know how much left. We know how much reacted. And that all reacted away. It was, I'm going to do a minus 0.4163 moles reacted away. So that we had 0. Oh, that's during the reaction. It's 0 moles, it's 0 grams, so I'm not going to worry about that right here. What I want to ask you about is how do we figure out what reacts away here? Well, remember when I set that up today, I said, well, during the reaction, we're gonna have that go away at a rate of 2x. While this one goes away at a rate of minus x. So then what would x equal? It's half of that. 0.2. 4-1. Oh, we have it. We have it. It's at 0.208. So that's how much reacts. We're subtracting that. Okay, so I've got 0.34686 minus 0.20815, and so I get 0.1387 moles left. And that, let's see, we had 3 here, 3 here. Okay, good. Oh, yeah, so that's 3 decimal places. There we go, and 3 sig figs. So remember in this step, I'm looking at the decimal places. This was also 3. And it happens to match this time. So that's moles of calcium carbonate left. So in order to figure out those grams, I'm going to take this molar mass and the moles left and combine those to calculate grams left. Okay, 9.998 to 3 sig figs is 10.0 grams. And that was with the underlined 9. Okay, the same number of moles was formed for the water, so I can take that same value, 0.1387 times 18.02, so we're going to get 2.5 grams here. And that actually came out to 2.499, but we'll have to round it up for 3 sig figs. Okay. All right, anything else? Yes, a little more. All right, so it's very condensed. You may have written out dimensional analysis for all of these, and I recommend that you do that. If you do that, if you get enough practice, then laying it out in a table is relatively intuitive. All right, let's see what the next part asks. Oh, calculate the mass of solid remaining after the reaction and after the water has been evaporated away as described in part B. Mass of solid remaining. Okay, there's our equation. I'm trying to view the equation there. Oh, right, okay. The solid remaining after reaction. So remember the instructions said that it's going to boil off the water. It's going to boil off all of that aqueous water too. So all of the aqueous acid. The only thing that's going to be left in there is what's left in there. So the new water is going to boil off. All of the other water is going to boil off. And so we're going to be left with the 10 grams of calcium hydroxide. Oh, yeah, I can scroll it back down now. So we're going to be left with the calcium hydroxide plus the calcium acetate. And so that should be 32.5 grams total salt residue. Okay, these are complicated, long problems. And I think this section of chapter 15 is probably not part of what the of the expected coverage. I'm not sure. It wasn't super clear, but judging from the OWL homework, probably this wouldn't be covered necessarily, right? So the reason I do is because the sooner that you are exposed to long, hard problems, the less overwhelming it is when you have to just, like, suddenly your life is long, hard problems. So this is a little bit optional. It would fall into the category of overstudying to make sure you can ace that final. It also helps solidify all these different things that we've learned when we see them wrapped together into one real life kind of problem. I thought these would be molarities, which are a little bit easier to work with. But this is useful because they're giving you that process of boiling off the water and asking how much salt residue is there. So yeah, that makes sense. Okay, well, that will be the end of our last worksheet. And I will see you online. And maybe in the department next quarter if you come around the Hazel Miller building. So have a great weekend and best of luck on all of your finals.